Today's lesson is on 5.1, key features of exponential functions. All right, I need you to recognize the difference between three equations. We have a linear, which is like y equals mx plus b, or y equals 2x. We have a quadratic, which has to have an x squared in it. And then we have to have an exponential. An exponential means the variable is the exponent. So you'll have like y equals 2 to the x power. We already know what a linear looks like. A linear is going to be a straight line, and a quadratic is going to be a parabola, a U shape. Today we're going to figure out what an exponential looks like. So the first parent function is y equals 2 to the x power. I'm going to go ahead and I'm going to start making a t-chart. Let's put some negatives like -2, -1, 0, 1, 2. Also do 3 and 4 here. This is going to be 2 raised to the -2 power. And keep in mind that a negative exponent makes it flip to the bottom. So it's actually going to be a y over 2 squared, which is 1 over 4. Here, this is going to be 2 to the -1 power, which is 1 over 2 to the +1, which is just a 1/2. 2 raised to the 0 power. Anything raised to the 0 power equals 1. 2 to the 1 equals 2. 2 squared equals 4. 2 to the third is 2 times 2 times 2, which is an 8. And then 2 to the 4th power is 2 times 2 times 2 times 2, which is going to be a 16. In the scientific calculator, you're going to have to use this key right here, the up key. So you would put in like 2 raised to the, now I'll type in 4, and there I get a 16. Now right here on the negatives, let's say I do 2 to the -1, 2 raised to the -1 power, and it's going to give you the 1/2, which is the same as 0.5. I'm going to go ahead and graph these points. Let's make sure we go up to 8. 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to go ahead and graph these points. At -2, it's 1/4, which is a 0.25, which is right here. -1 is going to be a 1/2. 0 is going to be 1. 1 is going to be 2. 2 is going to be 4. 3 is going to be the 8. And then 4 is going to be 16, which is way up here. This graph is actually going to look like this. It's never going to hit the x-axis. With that said, that means that this is going to be a horizontal tangent. Or asymptote, sorry, asymptote. That's a horizontal asymptote. Another key point is the y-intercept. The y-intercept is going to be 0, 1. And the reason why I'm stressing these two things about it is because we're going to be doing transformations here. And this is what you're going to want to be shifting. You're going to want to be shifting the horizontal asymptote along with the y-intercept. Now, let's see some key features on this. So our domain here. Our domain is going to be from -infinity to +infinity. You could type in any x value and you will get a solution. Now, as closer you get to the left, it's going to be 0. It's going to be 0.000001. So the domain here is going to be from -infinity to +infinity. The range, if you take this graph and you smash it on the y-axis, it's never going to hit 0. So because it's never going to hit 0, it's going to get really close to it. You want to make sure you put a parenthesis 0, because I'm not including 0. And then it's going to an arrowhead, which is infinity. And actually, we don't ever put +infinity. So just leave it like that. The y-intercept is the 0.01. Your asymptote is going to be the horizontal asymptote, which happens to be y equals 0. That is the x-axis. Now let's look at our end behavior. When you look at the end behavior as x goes to -infinity, what's happening to the y? And as x goes to +infinity, what's happening to the y? So as x is going to -infinity, the y is going to be a 0. And as x is going to +infinity, the y is going to infinity. So that's the parent function, y equals 2 to the x. Let's go ahead and now let's look at what happens when we have a 1/2 to the x. So on this one, notice how it goes from down here and it's increasing as it goes up. Let's see what happens here. I'm going to go ahead and make my t-chart again. I'll plug in a -3, a -2, a -1, a 0, a 1, a 2. Now this is going to be a 1/2 raised to the -3rd power. That negative exponent means this is going to flip. So it's actually going to be a 2/1, which is just going to be a 2. And instead of being a -3rd power, it's a +3rd power. And 2 to the 3rd power equals 8. Once again, the negative exponent is going to flip this, so it's going to become a 2 square. Anything raised to 0 power equals 1. 1/2 to the 1 is just 1/2. Now 1/2 square, 1 square is 1, 2 square is 4. Once again, I want to make sure I go all the way up to 8. -3 is going to be an 8. -2 is going to be a 4. -1 is a 2. 0 is a 1. 1 is a 1/2. A 1/4. Now this time it's going from +infinity down to 0. This one's going to have still this same horizontal tangent right here. I mean asymptote. I don't know why I keep saying that. And my y-intercept is still going to be at the 0.01. So right here, my domain is still going from -infinity to +infinity. My range, still again, if I smash on the y-axis, it's going from 0 to +infinity. I do not want to include 0. My y-intercept is still 0, 1. My asymptote is still going to be y equals 0. Now the end behaviors is where it's going to change. So let's go, x goes to negative infinity and x goes to positive infinity. So as x goes to negative infinity, the y is going to positive infinity. As x is going to positive infinity, the y is going to 0. So what I want you to notice is right here on 2 to the x, it's increasing on the tail end. But right here, how you have a 1/2, which is a number less than 1, it's decreasing at the end. Transformations. The number in the very, very front is going to be a reflection across the x-axis if it is a negative. If a is less than 0, meaning it's a negative. Now, keep in mind on the a value, if we're going to have a vertical stretch and a shrink, it's a stretch if the a value is greater than 1, the absolute value of it, and it's a shrink if it's a number between 0 and 1, which means it has to be less than 1, the absolute value. And then your shifts, the h is grouped with the x, so that's going to be your left and your right. So that's your horizontal shift. And remember, you're going to go the opposite direction. So negative goes to the right, positive goes to the left. And then the vertical, the up and the down, is going to be the k value on the side. Positive goes up, negative goes down. So here we're going to write the parent function and list the transformations. Now, the parent function is whatever the base is raised to the exponent without any numbers. So the parent here is just going to be a 4 to the x. Now starts the transformations. The 2 is right here. That's the h value. And it's grouped with the x, so that's going to be the left and the right. So negative 2 is going to mean right 2. And then the number on the side, the 5, that's the k value, that's up and the down. So positive 5 means up 5. Go ahead and do B and C right now on your own. Write the parent and any transformations. If you need to hit pause to do it on your own. I'm going to go ahead and go over the answers now. So right here, your parent is, there's the exponent. It's whatever the base is raised to the exponent. So that's going to be a 2/3 raised to the x power. The positive 1 is grouped with the x. So that's going to be the left and the right. So that's going to be a left 1. and the minus 7 goes down 7. Be careful on this one. The parent is whatever base is raised to the exponent. So that's going to be your parent right there. It's just 3 to the x. Now on this one, because it is a negative in the very front, the a value is negative. It's going to be reflection across the x-axis. Now the number 2, because the number 2 is greater than 1, that's going to be a stretch by 2. A vertical stretch by 2. And the plus 6 on the outside means up 6. Now we're going to start applying these to some applications, some word problems. Now we have exponential growth and exponential decay. It is easy to tell the difference between the two, because when you think of decay, you think of addition. So this is going to be a1 plus r raised to the t. And decay, we think of subtraction. So on exponential decay, it's still going to be a of t equals a1 minus r raised to the t. This number is going to be greater than 1. This number is going to be between 0 and 1. Now, a of t is going to be your final solution. The a is going to be your initial amount. How much are you starting with? Now, the a has to be greater than 0. The r is going to be your rate. The 1 plus or minus, that's going to be your growth or your decay or your base. R is going to be the rate as a percentage. Now you need to change this to decimal. And to change to decimal, you need to divide by 100%. So basically just divide by 100. So 4% would be 0.04. Okay, we're going to start off with an example here on the applications. Without graphing, determine whether the function represents exponential growth or decay, exponential decay. Then I want you to find the growth or decay factor and the rate of the increase or decrease. The parent function here is going to be y equals a 1 minus r raised to the t. That's going to actually be the time, okay? Now, on this one, the initial amount is going to be 5, but the question didn't ask me for the initial amount. It did not ask me for the initial amount. However, right here, I can actually set 2/3 equal to 1 minus r, and I can solve for the r. But from the very beginning, 2/3, that is less than 1. So because it's less than 1, it's going to be an exponential decay. So right here, if I take this piece, this is less than 1. So automatically, it's going to be a decay problem. Now, to find the decay factor, that is your decay factor. Okay, so my decay factor is 2/3. Now, how am I going to find my rate? To find my rate, I need to solve this. So now I'm going to set 2/3 equals to 1 minus r. If I subtract 1 to both sides, 2/3 minus 1 is going to be a negative 1/3. I'm going to divide both sides by a negative 1, so positive 1/3 equals r. So my rate of decrease is going to be a 1/3. I want to multiply that by 100%, and that gives me a 33%. I'll give you guys a minute. I want you guys to try this one next. This is greater than 1, so it's going to be a growth. Go ahead and try this one. If you're still working on it, go ahead and hit pause, finish it, and then hit play. I'm going to go and work it out. So right here, this piece is greater than 1. So this is going to be a growth. And then remember, this is going to be y equals a 1 plus r raised to the t. So right here, this is what we're solving. And then your growth factor is going to be the 2.1. I'm going to go ahead and solve this. So 2.1 equals 1 plus r minus 1 to both sides. So I get a 1.1 equals an r. So your rate of increase is going to be 1.1 times 100%, which is equal to 110%. We're now going to do another word problem, a real world one. A car was purchased for $24,000. The model is y equals 24,000 times 0.8 raised to the x. Or you could put raised to the t. We'll put raised to the t because this is going to be time. Can be used to represent the value over time. That's the reason why I wrote a t instead of an x. Now, right here, your decay factor is 0.8. It is less than 1. That's why it's a decay. And think about it. When you drive a car off a lot, it depreciates. It goes down. Is this a growth or a decay? And I just went over that. Right there, the base is 0.8, which is less than 1. That's why it's a decay. So the base is equal to 0.8, and that is going to be a decay. If the base is greater than 1, it's a growth. If the base is less than 1, it's a decay. What is the rate of decay? Now the rate of the decay is B is equal to 1 minus R. Well, the b is the 0.8, because remember that goes a, that's b minus, 1 minus r, and that's raised to the t. So the b value is going to be 0.8, which we knew right here. So I'm going to set 0.8 equal to 1 minus r. I'm going to subtract 1 to both sides, so I get a negative 0.2 equals negative r. Divide both sides by a negative 1, and I get a 0.2 equals positive r. Multiply that by 100%, so then I get a 20% equals the r. This is the original problem. And because it's a decay problem, this is y equals a 1 minus r raised to the t. That is the reason why this is what I solved. Now this is a little bit different. When will the value reach 5,000? So now I want to know the ending to be 5,000. So if this is my equation, I'm not giving you the time, I'm giving you the y value. So I want it equal to 5,000. Now, as of right now, we don't know how to solve this algebraically. So what we're going to do is we're going to use Desmos. We are going to look, because these are equal, we need to find out where they intersect. So you're going to go ahead and use Desmos or a graphing calculator. In Y1, you're going to type in 5,000. In Y2, you're going to type in the 24,000 raised to 0.8x. And then you have to find out the point of intersection. So let's go ahead and let's do that. Let me pull up my Desmos real fast. All right, I'm going to share my screen. All right, so right here, and the first equation, I'm going to type in 5,000. On the second equation, I'm typing in 24,000, parentheses, 0.8 raised to the x power. Now, if you notice, it's not popping up here. And the reason why I'm shifting it to the right is because my time has to be positive. I'm going to have to zoom out. And I basically have to find out when the y value equals 5,000. Okay, so there's 5,000. Let's see if I can pull it up right here. There's 5,000 right there. I want the y value to be 5,000. So it's about right there. It's about 7.0. There it is. 7.03. That's when the y value equals 5,000. So right here, I'm going to go ahead and say that the time, or the x value, is going to be 7.03 years. And if you want, go ahead and check your answer. Type in 24,000 times 0.8 raised to 7.03, and you're going to get really close to 5,000. All right, second to the last word problem. The population of made-up city was about 157,000 in 2015 and decreased at a rate of 0.8% per year. Calculate the expected population of the city in 2020. Keyword right here, decreased. So automatically, that's going to tell me 1 minus r. So my equation here is going to be y equals a 1 minus r raised to the t. They gave you the a, that's your initial amount. Your initial amount's right there. So this right here is going to be your a value. Your percentage, your r. Your r is going to be 0.8%. Now we need to change that to a decimal, and to change that to a decimal, you need to divide it by 100%. And that's going to give me 0.008. So now I can go ahead and plug in the numbers. I have y equals the a value, 1 minus the rate, which is 0.008. Now the time. On your time, you are going from 2015 to 2020. So on your time, you have 2020 minus 2015, so your time is going to be 5. So we are going to raise that to the 5th power. Order of operations says do parentheses first. 1 minus 0.008 is going to be 0.992. Next, you have to do exponents and then multiply. So let's go ahead and do that. My scientific calculator automatically does order of operations. Now, right here, we are talking about population. So I'm going to go ahead and I'm going to write the decimals for right now. However, when I'm answering this, because you're talking about population, you're talking about people, you cannot have 0.67 of a person. So that's going to round that up to a 20 right there. So in 2020, there will be about 150,820 people. Do not leave the decimal. And if it's talking about money, go to 2 decimal places. Think of the context of the problem. Last example. The population of a large city was about 4.6 million. In the year 2010, and grew at a rate of 1.3% per year for the next 4 years. A, I want you to write an exponential function to model the situation. B, I want you to find the population after the amount of time specified. go ahead and hit pause and fill out these two. And when you're done, hit play. I'll go ahead and I'll start now. So keywords, grew. That automatically tells me it's y equals a1 plus r raised to the t. Now the initial amounts right here, because it says the population of a large city was about 4.6 million. So that's going to be your A. This right here is going to be your R. So I'm going to have y equals the A value. The A value is the 4.6 million. 4.6 million is 4,600,000. Now your rate is 1.3%. I'm going to go and divide that by 100%, and I get 0.013. So 0.013 raised to the time. If I go ahead and I add those up, I get 1.013 raised to the t. So here is my exponential function that models that situation. And now on part B, it wants the time specified. Right here, it tells you 4 years. So the time is going to be 4 years. So I'm going to go and plug in the number 4 here. Four, 6, 0, 0, 0, 0, 0, 1.013 raised to the 4th power. I get a 4843904.956. Going back to the context of the problem, you're talking about population, so this needs to round to the number 5. I'm going to answer in a complete sentence. The population will be about 4,843,905 people in 4 years. And that concludes our notes.